Hello, today we are going to finish this section 11.3. The title of the section is Application Analysis of Algorithm Efficiency 1. In the last class, I discussed the first part of the section. Today, I'm going to discuss the second part of the section. This is chapter 11, Analysis of Algorithm Efficiency. First of all, we are going to discuss uh, very important sorting algorithm. This is called the insertion sort. Sometimes you might be familiar with this. This is the insertion sort. Let me read the slides first. Insertion sort is an algorithm for arranging the items in an array into ascending order. All right. In this class, we are just working on the ascending order, but insertion sort can be used to order them in the descending order. All right. So it doesn't matter whether you arrange them ascending or descending. You could just use the insertion sort. But in this class, we only consider ascending order. All right. This is in this class. All right. Initially, the second item is compared to the first item. Let's say you have these items in your array. This is A1, A2, A3, A4, A5, and A6. In this sorting method, we first compare first and second elements in the array. If the second item is less than the first, their values are interchanged, and as a result, the first two array items are in ascending order. All right. If first we compare these two, the first two elements in the array, if they are not in the ascending order, we switch them. All right, we switch them. So the array will look like this. A1, A2, A3, A4, A5, A6. Now we interchange A1 and A2. So this will look like A2, A1. All right, and we keep on doing that procedure. The idea of the algorithm is to gradually lengthen the sorted section by inserting each subsequent array into its correct position relative to the preceding one. All right. So this is the given. This is the given array, and this is the array in the second step. In the third step, you compare this with that. Okay, if they are in not in the ascending order, so you switch them and so on. Okay, so this is called the insertion sort. We are going to learn insertion sort with details soon. For now, just keep this summary in your head. Later, we can just understand this. All right. So let's go down. The insertion sort algorithm. When the last item has been placed, the entire array is in that ascending order. Okay, so we just keep on doing this. And finally, we have the array of the ascending order. It might be something like A2, A1, A3, A5, A6, and A maybe 2. Okay, let's consider that as the ascending order of the elements. All right, so that is what I explained here. When the last element plays, it is in the ascending order. Don't worry, we are going to discuss this algorithm with details in this presentation. Now you have a figure here. Figure 11.3.2 illustrates the action of step K of insertion on an array A1, A2, A3, AN. Alright, so this is the given array to you. So this array represents a set of numbers. And then at the kth step, the first k minus 1 elements are already sorted. Okay, they are already sorted. Now you have to place this element according to the order. This element might be placed here, maybe placed there, maybe placed here. Okay, who knows? It might be placed in the appropriate location. All right, so this is the insertion sort. All right, so we're going to discuss the algorithm now. This algorithm explains all about the insertion sort. Let me read this. The aim of this algorithm is to take an array A1, A2, A3 up to AN where n greater than or equal to 1 and reorder it. The output array is also denoted as this A1, A2, AN. It has the same values as the input array, but they are in ascending order. Okay, but they are in the ascending order. In the kth step, A1, A3, AK minus 1 is the ascending order, and AK is inserted into the corresponding position. Okay, AK is inserted into the correct position. Okay, so this is the basic idea of the insertion algorithm, insertion sort. Let's go to the algorithm. I'm going to explain this algorithm by using an example right here. So it is easy to understand this example by using an algorithm. It is easy to understand this algorithm by using an example. Because of that reason, I have just included an example here. So this part, I just copy the body of the algorithm. I just copy this one over here. All right, so I can explain it step by step. This is the given array to you. 6, 3, 5, 7, and 2. Those are the given. This is the given array, and here you have the algorithm. All right, so I'm going to use that algorithm to sort the given array. So the first column is representing the corresponding entities. These are the elements of the array, and then K is an index, X is a value, and J is an index. N is number of values in the array. All right, so let me mark them. This K is right here. All right, and then this X is right here, and then this J is right here. All right, and also J is related to that. All right, so let's go forward. At the beginning I just write these elements. It is 6 right here, 3 right here, 5 right here, 7 right here, 2 right here. Okay, so I wrote those elements, and then there are 5 elements. Okay, n equals 5. At the first iteration, or even before the first iteration, you had initialized k. Here at the first iteration, k is 2. You can see it here. K is 2. K goes from 2 to n. At the first iteration, k is 2. Okay, I just wrote k as 2, and x is 3. Here x is the second element. Okay, which is the second element is 3. I wrote 3 here. J is k minus 1. That means 2 minus 1, which is 1. Alright, so let me take these circles out. Alright, now that is the those are the index values and the x, and then we go to this while loop. We check whether j equals 0 or not. J does not equal 0, so we go inside the while loop, and then it says if x should be smaller than aj, j is 1. All right, j is 1. That means here aj should be 6. All right, aj should be 6, and x is that 3 less than 6. All right, so that means the if loop is satisfied. This if loop is satisfied. All right, now you go inside the if loop. Then what you have to do is you have to execute these 2 lines. These 2 lines give me a second. These 2 lines explain switch or let me write in different way. This means replace aj plus 1 with aj. There are 2 things. This is the first thing you do, replace and the second thing is replace aj with x. Okay, if you go inside the for loop, this replacement will occur. Okay, that's technically you switch 3 and 6. Okay, that is technically you switch 3 and 6. Okay, that's what you have here. You switch 3 and 6. Now you have 3, 6 are switched, and the rest of the elements are same. Here you have 5, here you have 7, and here you have 2. That's it. Okay, these 2 elements 6 and 3 are switched, and now at the end you have j equals j minus 1. That means the index of j is reduced by 1. Then you will get j to be 0. All right, j0 means while loop stops. See, while loop stops. All right, then in the next round you are going to the next k value, which is 3. Next k value is 3. You can see it goes from 2 to n. You have already gone through 2. Now you have to go to 3. K equals 3, and then x equals that ak. That means this element 5, which is right here, and then j should be k minus 1, which is 2. All right. Now again you have to do the comparison. You are going inside the while loop, and then you check aj, which is j should be 2, aj should be a2, that means this is aj, that means 6. All right, so because already 3 and 6 are interchanged in the previous step, now it is 6, not 3. All right, aj should be this element, which is 6. Now we have to compare 6 with 5, which is x. 5 greater than 6. Now you go inside the if loop. Okay, you go inside the if loop and then you interchange them. All right, so you interchange these two elements. Okay, then you have here you had 6 5, now you have 5 6. Now let me write the rest of the elements. This is 7 and this is 2. All right. It is kind of frozen, I don't know why. All right, good. Now you move to the next step. In the next step, you get j equals 1. All right, now j equals 1. Now you are comparing your new x, which is your new x which is already 5, and you just compare 5 with 7. Actually, you compare 5 with 3 here. Let me write that 3. You have 3 here. So you just compare this 5 with 3. So you don't need to interchange them because they are in the proper order. So you write 3 and 5 because they are in the proper order, 6 7 2. So this is the current order of the elements. I just remove this one because I just want to show you not interchange didn't happen here because they are in the order. 3 and 5 are in the order. All right, they are in the ascending order, so you do not switch them. All right, in that case your j is 0, so this while loop stops. All right, and then you move to the next k value, which is k equals 4. All right, if k equals 4, x equals the fourth element in the array, which is 7, and j equals 3. J equals k minus 1, which is 3. All right, let's move to the next iteration. Now you have 7 here. We have 7 here. You're going to compare this 7. First you compare this 7 with that 6. Okay, 7 is bigger, so you don't switch. And then since 7 is bigger than 6, 7 is bigger than all these rest of the elements. Okay, so 7 is already in the proper order. Okay, 7 is already in the proper order. Order is 3, 5, 6, 7. 7 is already in the sorted order, in the ascending order. So you do not switch anything in this iteration. All right, so that means if loop doesn't satisfy, let me write it down here. Here, AJ, which is, give me a second, 6, and X is 7, that doesn't happen. So the if loop doesn't work here. Okay, you do not go inside the if loop. So let me rearrange this a little bit. All right, let's move to the next step. Let me write down the proper order here. The order is same as before, which is 3, 5, 6, 7, 2. Okay, now K is 5, and in that case X is just the last element, which is 2. Okay, J is 4. All right, then you are just comparing these two elements in the first attempt. They are not in the proper order, so you switch them here. Okay, and then you just compare. Let me write the rest of the thing here. 3, 5, 6. Okay, now you just compare this 3 with 2 with 6. They are in the not in the proper order, so you just switch them. Here you switch them. Okay, let me write the rest of the element. 3, 5, and then you compare these 2 with 5. They are not in the proper order, you switch them. And finally you just compare 2 with 3. They are not in the proper order, you switch them. Okay, finally you have the order. Let me write the rest of the elements. So this should be 7, this should be 6, 7, this should be 7, 6, 5. So finally you have the sorted order, which is right here. Okay, so this is the sorted order. Okay, so this sorting algorithm is really easy. You can understand once you read again. This gives you extra information. This slide gives you extra information about the sorting method. You can read it and understand if you need. I mean, I already explained this. In the above algorithm. So this is by words. This explains how the algorithm works by words. All right, so let's move to the next example. In this example, we have to find worst case order for the insertion sort. Let me move to the first part of the example. When insertion sort is applied to the array a1, a2, an, what is the maximum number of comparisons of those that control while and for next loops are included in the count? All right, so you have to include 2 loops only, The first loop is while loop, and then for loop. All right, you have to include those two loops only. So there's if loop, you yes. So once you include these two loops, actually if loop is also included inside. Okay. Once you include for loop and while loop, if loop, you can see if loop is already inside. So you have to consider a number of comparisons. All right. In the part B, you have to compute the polynomial order to find a worst case order for insertion sort. All right. Let's do the first part. First of all, we have to understand how the comparisons are done in this algorithm. I see there are two lines where the comparisons are done. In this line, comparisons are done, and that line, comparisons are done. All right. Let me write in these two lines, comparisons are done. All right. So you have to consider those two lines when you count number of comparisons. Okay. Let me read the next slide. For each iteration of while loop, one explicit comparison is made to test whether aj is greater than x, which is right here. Okay, so you check whether aj is greater than x. All right, that's true. During the time that ak is input to the position relative to a1, a2, ak minus 1, the maximum number of attempted iterations of the while loop is k. Okay, there are k iterations in the while loop at this point. There are two points here. The first point is when ak is less than every these numbers and result in k minus 1 comparisons. All right. Why there are k minus 1 comparisons? Here you are considering the worst case scenario. Let me go back. It's the maximum number of comparisons. All right. It's the maximum number of comparisons. That is the worst case scenario. Worst case. All right, you are considering the worst case scenario. That's why we just use the word maximum number of attempts or the maximum number of comparisons. All right. All right, so the here, let me write that things here too. The worst case. The worst case scenario happens, your array is in the reverse order. Okay, let's say you are just making this array into the ascending order. Now your array is in the descending order. All right, let's say the numbers in the descending order, maybe 6, 5, 4, 2, 1. All right, the numbers are in the descending order. So that is the worst case scenario. All right, so you have to make k minus 1 comparisons in order to input ak. All right, so you're going to input a new value. Let's say you are going to input number 7. or maybe you're going to just work on this number 1. You include this number 1, then you have to compare 1 with this, and then you have to compare 1 with that, and then you have to compare 1 with this. Okay, and finally compare 1 with 6, and then you have to bring 1 forward. Okay, you have to bring 1 forward. So in that case, you have to make k minus 1 comparisons. All right, keep that in mind. That is in the if loop. That those comparisons are in the if loop. And then we're going to discuss about the while loop. The while loop checks whether aj equal to 0. All right, that's also a comparison for every iteration in that loop, right? Then every iteration outside of if you check whether j equals 0. So then for every k, this adds one value of complexity. Okay, just one comparison. That adds just one comparison for every k. So that's what I have written down here. The while loop checks whether j equals 0 comparisons for every iteration in the loop, adding one more comparison. All right, here there are k minus 1, here 1. If you add them, it equals k comparisons. All right, so the maximum number of comparisons will be k for the kth iteration. Okay, that's for the kth iteration. Now there are how many such iterations like this? How many such iterations? The iterations run from 2 to n. When k equals 2, you have 2 here. When k equals 3, there are 3 comparisons. K equals 4 comparisons. When k equals n, there are n comparisons. So you have to add these numbers. What we do here is we just add 1 here and we subtract that one over there. So you will get the same series as before. So this equals that, they are equal. So you just add 1 here and subtract 1 here. The reason for that is by doing, you will be able to get this series which goes from 1 to n. You know how to compute this sum, which is calculus 1. That is actually half times n minus 1. And then this minus 1 is right here. Okay, so you simplify this, you will get that as the number of comparisons for an array of n elements. Okay, the part B says use the theorem in polynomial orders to find the worst case order for the insertion sort. Now you're going to compute the order. This is a polynomial. Since this is a polynomial, order for that one is theta n square. Okay, that's a theorem we have learned already. You see this n square. That n square equals this n square. Okay, then the worst case order of the insertion sort is n square. All right, let's go to the next slide. In the next slide, we have the next example. Example 11.3.7, finding an average case order for insertion sort. Now this is the average case. As you remember in the previous example, we discussed worst case. Now it is average case. All right, average case is harder than the worst case. Let me read this. What is the average number of comparisons that are performed when insertion sort is applied to an array of a1, a2, a3, an? Use the theorem on polynomial orders to find average case order for the insertion sort. Alright, so this is the given example. Alright, here you have the solution. For this solution, we just incorporate an idea which is called the expected value. So here you have to find the average case order. So average case equals the expected number. Okay, so the average, let me write again. Equals expected value. Alright, keep that in mind. Average equals expected value. That's why we are working on expected number here. For any positive integer n, let en be the average. En be the average. This is actually the expected value. Okay, or expected. Average or expected, both are same. Number of comparisons used to sort that array with insertion sort. Then for each integer k goes from 1 to n. So we have this equation. You have learned this in discrete math 1. Here you have the expected number of comparisons used to sort that. Expected number of comparisons used to sort this array equals the expected number of comparisons used to sort this array plus expected number of comparisons used to place ak into position relative to that. Alright, so I believe you can understand that. So you have this array. Let's say this part is already sorted, the beginning part is already sorted. Let's say this is already sorted. Then you have to insert that element. Alright. Expected value of this one is ek. Let me use it as a k minus 1. The bigger one is ek. This is ek. Expected number to sort k elements. This is ek minus 1. Expected number of sorting k minus 1 elements, and then you have to insert this element. All right, it might be here, 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 who knows, here, or maybe here. That is given by this equation. Let me read it again. The expected number of comparisons to sort this bigger array equals expected number of comparisons to sort the smaller array plus expected number of comparisons to place ak in the sorted order. Okay, in this sorted order means in this orange color part. All right. So we denote this by ek. Let me color this. We denote this by ek. Let me mark ek. This is ek. That is ek. Okay, this is ek plus 1. This is ek plus 1. Sorry, ek minus 1. Okay, and this is this. This is simply that. All right, so here we set up an equation. Now we have to find an equation for this black color part. All right, then we can just use telescoping series approach that I'm going to explain very soon. In the next slide, what we are going to do is we are going to set up an expression for this. You have to set up a mathematical expression for that, and then we just use the telescoping series approach to solve this equation that I'm going to explain very soon. First, let's talk about E1 here. E1 is the expected value when you have one element in the array. If you have just one element in the array, the average of that one is just 0, right? You don't compute average of one element. You need at least two elements to compute the average, which is the expected value here. So it is 0. That's why we mark this as 0. All right. Also, E1 equals 0 because when there is just one item in array, n, that means n equals 1, no iterations of the outer loops are performed according to the algorithm. Okay, when you have only one element, no iterations are performed. All right, so go to the next point. Now, at the time while loop is used to place ak relative to a1, comma a2, comma dot 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 ak minus 1, on average, the value of ak is equally like to belong in any of the k positions. Let me explain what are the k positions here. Now you have a1, let's say this is a1. This is a1, this is a2, and this is a3 dot dot, and then this is an. All right, so there are k positions here actually. The first position is this, first position, and this is the second position, and this is the third position, and this is the fourth position. Like that, this is actually I'm sorry, I have to make n minus 1 here. So I have to make k minus 1 here. That's what I'm talking about. Here it is k minus 1, location is k minus 1. And then here this location is the kth location. Okay, so there are k locations for this array. Either you can replace ak here before a1, or between a1 and a2, between a2 and a3, and between a3 and a4, blah blah blah, and then oi at last after a k minus 1. So there are k positions to place the new element. All right, so this is the new element, which is a k. This might go here, 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 or finally over there. Or there are k positions. That's what I'm saying. There are k positions. All right, the likelihood is equally. There are equally likely 4 positions. So that means inserting this to that location is same as inserting that to this location, inserting this to this location, and inserting this to that location. That means equally likely. That means inserting that element into any of the k positions is equal. Alright, so that's called equally likely. Thus, the probability of belonging in any particular position is 1 over k, because there are k positions. The probability of placing that one is 1 over k. If it actually belongs in position j, then you have to perform this many comparisons. K minus j plus 1 comparisons will be used to move it. All right. So it is given by the theorem. It is in the j's position, so that many comparisons are made. All right. Alright, there are k minus j plus 1 comparisons will be used to move it, because there will be k minus j plus 1 attempted iterations of the while loop. Actually, we have shown this one, this result in example 11.3.6. That is the previous example. We have shown this number in that result. All right, keep that in mind. Go to example 11.3.6 so you can understand how many attempted iterations are here. Okay, which equals k minus j plus 1 according to example 11.3.6. All right, now go to the next slide. In the next slide, you have a theorem from probability that gives you the expected value. According to the definition of expected values given below, so this is the definition, the expected number of comparisons used to place a k relative to a1, a2, a k minus 1 is therefore given by this equation. All right. That is actually by using this theorem. These are the numbers we have, and these are the probabilities. And these are the probabilities. In our case, all these probabilities are equal. In our case, P1 equals, P2 equals, P3 equals Pn equals 1 over k, which is right here. All right, and then these real numbers are given by that equation or this algebraic expression. Okay, this algebraic expression that is given in example 11.3.6, which is right here. Okay, which is right here. All right, since you know this number and those numbers, you can just put them in an equation like this, which is the expected value. Okay, so this is the expected value. All right, so that is this equation. Now what you have done here is we have taken 1 over k out, and then you have this here, and then we are going to simplify it. Let me write it again here, which is 1 over k sigma k minus j plus 1. This is j goes from 1 to k. Alright, so you can expand that. When j equals 1, you get k, just k here. When j equals 2, you get k minus 1, and blah blah blah. When j equals k, you get just 1. Okay, that is just the expansion. And then you can compute this part as that we have already done in the previous slide, and then simplify this. You will get it to be k plus 1 over 2. Okay, so that is that is the value for this paragraph. Okay, that is the value for this paragraph, which is right here. Let me write I will mark this as asterisk. This slide number 13, asterisk of slide number 13. So let me mark it here. Solution for asterisk in slide number 13. Alright, so you can just refer back. Okay, now you just substitute that one over there, right here, which is you have ek minus 1, and then that thing. So I'm gonna substitute everything back over there. Alright, so you get ek minus 1, then k plus 1 over 2, and you already know that E1 is 0, that we have already shown. Okay, go to next slide. And then we are using the telescoping series approach. Okay, so this is telescoping series approach. You have learned this in Calc 2. This is telescoping series approach. That you learned calculus 2. Okay, before going to the telescoping series approach, let me write this as ek minus ek minus 1, k plus 1 over 2. Alright, so then you see that it is E2 minus E1. Then in that case k equals 2, so you have 3 over 2. When k equals 3, you have E3 minus E2, and then it is 4 over 2, and so on. Give me a second. Okay, now you can see, you can cancel this with that, and then you can cancel this with that. If you just keep your eye on the same pattern, you could cancel this with some term here, you could cancel this with some term there. Those I haven't written down, right? So you could imagine how the cancellation happened. Now you just sum them up, and then you have this term E1, which is right here, and then you have En, which is right there. All right, and then sum all these numbers. Sum all these numbers, you have them right here. All right, and then E1 is 0, you know that. This one is 0, so you have En equals that series. So you just simplify that like that. This is simple algebra, so you can simplify En to be this expression. Okay, En to be that expression. Now we have to move to part B. Let me read the part B again of this example. Part B says, use theorem on polynomial order to find an average case order for the insertion sort. All right. So you already have a polynomial which is right here. Now what you have to do is you have to just use the theorem that we have learned before. Since the highest order of n is n square, the order of the polynomial is n square. That means the average case order for the insertion sort is theta n to the power 2. All right, so that is the end of that example, and also that is the end of the section. Thank you very much.